Okay, so for the next few class periods, we're going to talk about earthquakes. I was trying to decide whether to talk about volcanoes or earthquakes at this point, and after kind of looking at the notes, it seems like earthquakes is the next logical step to take here, because a lot of the information we just talked about, plate tectonics, sort of plays into this topic as well. How many of you have been in an earthquake? Anybody in class been in an earthquake? Where?
I used to live in California.
Yeah, what part?
Los Angeles.
Okay, so Los Angeles area.
Yeah.
Very tectonically active. Anybody else? What's the biggest one you were in down there?
Oh gosh, I don't remember.
Some big ones?
Not as big, but
Yeah, I've never really lived in earthquake country. The biggest one I've been in was a magnitude 6 in Guatemala. That was pretty fun. It rolled for about 45 seconds, and I don't know if you haven't been in an earthquake, time really goes slow when you're in an earthquake. Seems like forever. And it's weird. I mean, you get used to the ground being a stable feature. You walk, it doesn't move, and during an earthquake, it just feels like jello. I was in another one that was only a magnitude 4.5, but I was only a mile from the epicenter, and it literally threw me out of bed onto the floor. So that was kind of cool. But I haven't been in a big deadly one, which gets scary and unfortunately create a lot of damage and can kill a lot of people. So I think one of the biggest misconceptions about earthquakes is that it's any shaking of the ground. You know, when you get a big earth-moving equipment or a bomb that goes off and the ground shakes, that's an earthquake. Actually, according to geologists, that really isn't true. So one of our misconceptions that I'd like to sort of get past is that anytime the ground vibrates, it's an earthquake. According to geologists, that's not true. There's a really sort of specific definition, and that is that the shaking, in order to get an earthquake, the shaking has to come from energy released from rocks. And what that means practically is rocks have to break. When rocks break, they give off energy. I don't have a pencil with me, but imagine I have a pencil right now, right? And I start bending it. Let's say I put it behind my back, okay? I'm bending this pencil behind my back. And I'm going to bend it till it breaks. Are you guys going to know when it breaks? How are you going to tell? By the sound, right? When it snaps, what happens is that wood is bonded together. And to break it, you have to break those bonds. And when you break the bonds, it gives off energy in the form of sound. Earthquakes are exactly the same way. The rock bends the rocks to the point where they break, and then those bonds that had held the rock together release energy as seismic waves, but the seismic waves are really similar to sound that are traveling through the ground. So you can think of an earthquake as being the sound of broken rocks. That's really all it is. So just think of the pencil example, because it's really similar to how that works. So here it's kind of a fancy term, energy released from rocks. Well, it's really the sound of rocks breaking and that being transmitted through the earth. It's a little more complicated because sound waves are pretty simple. Earthquake waves are actually really complex. There's several different kinds of earthquake waves. And that's because rock is a little different than air. We'll get into some of it, not all of it. But think of it as the sound of rocks breaking. Geologists have learned a lot about earthquakes. And unfortunately, there's still a lot we don't know. We can't predict earthquakes very well at all. We're just not good at it. We don't have enough understanding where we can reliably predict an earthquake for people, which would be really nice to do because most of the world lives within an area that can be affected by earthquakes in a negative way. There are things we just don't understand. This is kind of interesting. There was a study about 20 years ago that said that during El Nino years, and we're not going to get into the in-depths of El Nino, but most of you have probably heard of El Nino, right? It's basically a weather pattern that's created by a switch in an ocean current in the Pacific. Bottom line is, during El Ninos, our weather gets all messed up. And we really don't know what causes El Ninos. They come up every couple years to every decade or so. Every couple years, every decade, this ocean current that runs between South America and Indonesia switches directions. We don't know why that happens, but it affects global weather. What's interesting is that when El Ninos pop up, there seems to be a higher than normal number of earthquakes in the ocean. Now, scientists are really fond of saying that correlation does not equal causation. Just because two things are related doesn't mean that just because two things are correlated doesn't mean that they're related. Perhaps this is just a coincidence. But some people have suggested, maybe El Ninos are actually caused by a greater number of submarine volcanic eruptions occurring, and that the earthquakes are simply a consequence of all this new volcanic activity in the ocean, and that's what affects the ocean current. We don't know this for sure. In fact, I would think most scientists probably don't buy into this idea, but it's something that's still being looked into. Sadly, as I said before, earthquakes still remain very unpredictable. We just don't have good, reliable ways of predicting when an earthquake is going to occur. There are some obvious myths that are associated with earthquakes. Especially if you live here in the U.S., probably the most common one is that California is going to slide off into the ocean during a big earthquake. That's not going to happen. That's not the kind of plate boundary that we have in Southern California. We have a transform boundary in Southern California where the two plates slide past one another. One side isn't going to drop off into the ocean. You might get small landslides along cliffs into the ocean during earthquakes, but it's not like a whole state or a big part of the state is just going to slip off and leave Arizona with oceanfront property. That's not going to happen. It's the wrong sort of tectonic boundary in Southern California. If you've ever watched any sort of Hollywood film on earthquakes, it always happens. The earthquake happens, these giant cracks pull apart, people fall into it. People are always falling into giant cracks in Hollywood films. Swallow up always the bad people, Sodom and Gomorrah type stuff. Cracks can happen during earthquakes. They're generally not very deep. They're generally not very wide. You just see sort of cracks in the ground where the ground is shifted. I've heard a lot to say, I don't want to move to California because of the earthquakes. Well, as it turns out, California does get probably a larger than normal proportion of large earthquakes, but because they do, cities and governments in California have changed their building standards. You have to make buildings that are strong enough to withstand earthquakes of a certain size. Engineers have standards that they have to follow when they build large buildings. Homes have to be built in a certain way. Here in Colorado, we don't build things the same way because we don't have the same earthquake risk. And yet what's interesting is we can get magnitude 7 earthquakes in Colorado. The biggest earthquake on record in Colorado happened back in the late 1800s, actually, over by Fort Collins, magnitude 7. Nothing around here is built with earthquake in mind today, but if we had a magnitude 7 that happened right here, there'd be some major damage. Same size earthquake in Southern California, not big at all. The biggest earthquake that happened in North America during recorded history didn't happen in California, didn't happen in the Pacific Northwest. It happened in Missouri. We'll talk about that earthquake quite a lot. It was probably near a magnitude 9. Magnitude 7s are really scary. Magnitude 7s kill people. Magnitude 8s are ridiculous. Magnitude 9s are off the chart. And back in the early 1800s, Missouri had a magnitude 9. It was so powerful that it rang church bells 1,000 miles away in Philadelphia. The Mississippi River flowed backwards for a few hours because it shifted the land. Boats were literally thrown out of the Mississippi River onto shorelines. It's a crazy big earthquake. And yet, if you go there today, there's not a lot of buildings that are built to withstand large earthquakes. And there's some evidence that that earthquake system goes off every couple hundred years. And it's been a couple hundred years since the last one. So we have areas in the U.S. that you could argue are far more dangerous than California. Might not have them as frequently, but they can have them as big, and the buildings aren't built to withstand them. Okay, so like our other topics that we've talked about in here, what we'll do first is do some of the science-y background stuff so that you understand how the process actually works. And then next class we'll get into more of the death and destruction and mayhem parts of it. So causes. What causes an earthquake? It's pretty simple. We just spent some time talking about plate tectonics. We know that the Earth shifts around, and as these huge continental and oceanic crustal plates move apart from one another, slam into one another, slip past one another, it puts stress on the rock. It puts rocks under pressure. Those divergent areas, you get rocks that are being pulled apart. Those convergent areas, you got rocks that are being pushed together, being squished. Those transform boundaries, you have areas that are being sheared apart one another. All of those intersections put the rock under stress. And rocks are pretty strong. You guys know how strong rocks are. If you've ever tried to break one with a hammer, it's not easy. You got to beat the crap out of it, right? But if the Earth puts enough stress on the rock, if the stress exceeds the strength of the rock, it'll break. Again, think of the pencil, right? If you have a pencil, I used to do this when I was bored in second or third grade. We always had to have our 20 number 2 pencils, you know, little shopping list beforehand. I used to sit and bend my pencil and kind of see how far I could bend before it would break. And that's what happens with rocks too. When you start to stress them, they bend. But eventually you'll get to the point where you're putting so much stress on that you're going to exceed the strength of the bonds, in this case in the pencil, or in the earthquake case, the rock, and it'll break. And when it breaks, energy is released from those bonds. In the pencil example is a sound wave, or in the rock example is seismic waves. So rocks are put under stress from the movement of the Earth's plates. They bend in response to that stress. And if you end up stressing them enough, they're eventually going to break. And when they break, they're going to give off energy in the form of these seismic waves. So when the stress exceeds the strength of the rock, they break. And when they break, energy is released as seismic waves, and it travels outward from the broken rocks. Now, sometimes the break can be so powerful that the seismic waves will travel all the way through the Earth to the other side. They can be felt worldwide. Other times they're small. You might not even feel them if you're close to it. I study volcanoes. Volcanoes make lots of rock breaks, lots of tiny earthquakes. And when I'm working on them, I literally can't feel most of them. Go back to the office after the day and, oh, there were 30 earthquakes while you're out there working today. I didn't feel a single one. They were low in magnitude. We'll talk about magnitude here in a minute. But every once in a while, you'll feel a few that are big enough. Okay, this is the most important part of the background right here. So if you're starting to doze, undoze. This is the part you'll want to know. When we broke the pencil, we talked about sound wave, okay? Earthquake waves are similar, but they're a little more complex. We actually have several types. We're going to talk about two main types because they allow us to do some pretty neat things scientifically that we'll get into. So the two main kinds of seismic waves are first the P waves. P waves stand for primary waves. These waves are much like sound waves. They are a compressional wave, and I'll show you a diagram here on the next slide. That shows what a compressional wave actually looks like. But these buggers are fast. You're not going to outrun an earthquake. P waves travel 9,000 to 15,000 miles an hour. Depends on the rock type. Generally, the denser the rock, the faster these P waves move. And it'll move through anything. It'll move through liquids. It'll move through solids. So P waves, super fast, compressional wave, move through solids and liquids. At exactly the same time that a P wave starts out, the second kind of wave called an S wave, which is a secondary wave or a shear wave. And I'll, again, here in a second, show you a diagram of how it behaves and looks a little different than a P wave. S waves are relative slowpokes compared to P waves. Roughly half the speed, 4,500 to 8,000 miles an hour, still ridiculously fast. And what's interesting is they can't travel through liquids. They won't travel through molten rock. Remember last class we talked about the zones within the Earth? The crust, the mantle, the outer core, the inner core. It's actually these S waves that tell us that the outer core of the Earth is liquid. These S waves can't travel through the outer core. The P waves can. So if you're on the other side of the Earth from a big earthquake, there's a big earthquake on one side of the Earth, you're on the other side, you'll feel P waves. You'll feel no S waves at all. And I'll show you a diagram that sort of shows how the liquid outer core dampens or gets rid of our S waves. Okay, a couple of terms for you, hypocenter and epicenter. A hypocenter is the actual place within the Earth that breaks first. This is where the rock is actually breaking down in the Earth. Sometimes earthquakes are shallow. They're only a few miles beneath the surface. Sometimes earthquakes are really deep, 50, 60, 70 miles beneath the surface. Where it is beneath the surface, that's called the hypocenter or focus. Now, it's difficult to describe somebody. If there's an earthquake out in California, you can say, well, the hypocenter is down here in the ground. But people kind of want a map location for their earthquake. So we have a related term, which is called an epicenter. And I'm sure most of you have heard of the earthquake epicenter. That's not where the earthquake actually occurs, but it's directly above it. It's a point on the Earth's surface directly above where the rock breaks. And we'll usually identify the epicenter as the nearest town. So back in 1989, actually I think it was October 16th, 1989, there was a big earthquake in the Bay Area region of California, up around San Francisco. Canceled the World Series. Happened right at the beginning of one of the World Series games. And the hypocenter was directly beneath a little suburb called Loma Prieta. So the epicenter was directly above it. So the epicenter for that earthquake was Loma Prieta. It's called the Loma Prieta earthquake. Sometimes you get them directly beneath, like Northridge, California. That'd be the Northridge epicenter. If something happened directly beneath Greeley, the point beneath us is the hypocenter. The epicenter would be right here in Greeley itself. So epicenter is just the map location on the surface directly above where the rocks break. Now, probably another misconception is that the closer you are to the epicenter, the more hazardous conditions you're going to be in. That's not exactly true. Epicenters do not always sustain the most damage during an earthquake. There's a lot of other factors at play. One is anybody living near the epicenter? If nobody's living there, there are no buildings there, there's not going to be a lot of damage. Maybe there's a city 8 miles away with lots of people, lots of poorly built buildings, and maybe it'll sustain a lot of damage, but it's not the epicenter itself. And a lot of these breaks occur along fault lines. A fault line is simply an area of the ground that is broken before, and it's easy to re-break it. And these fault zones sometimes exist at various angles under the ground. I think I have a diagram here that'll show it to you. First, before we get there, this kind of goes back to one of our earlier slides. It shows that we're going to put some stress on the Earth. We're going to stress the upper block of this diagram. The first things that rocks do, just like pencils when you stress them, is they bend. And when you have enough stress that exceeds the strength of the rock, they break, and then the rock shifts in response to it. Here's the diagram I was just talking about. So you can see here's the focus down here in the ground. That's where the rocks break. Sends out seismic waves in all directions. The epicenter is point on the ground directly above it. But in this case, you can see the fault angle is maybe 45, 50 degrees here. So the fault surface actually intersects the Earth's surface some distance away from the epicenter, right? So over where the fault intersects the Earth's surface, you might get a lot of damage through here as this whole system shifts. And you might not get nearly as much damage directly above it. So epicenter, again, only tells you the spot on the Earth directly above where the rocks break. Now there's likely to be damage there if there's a big enough earthquake, but it definitely isn't the case where the epicenters always receive the most damage. It's a little diagram of what a P wave looks like. It's a little compressional wave. It's just like a sound wave. Sound works the same way. I'm talking right now. What I'm actually doing is my vocal cords are compressing air, and that compressed air sends out in all directions and interacts with your eardrum, and your brain can perceive it as sound. That's what's happening here as well. During the earthquake, during the break, you get a little bit of compressed rock, and that little compressional package of rock moves out very quickly. Remember, it's 9 to 15,000 miles an hour. So P waves act just like sound waves do. Here's what an S wave looks like. It's got some serious up and down motion. It's not a compressional wave, it's a shear wave, it's a sine wave. And if you really get into this stuff, there's R waves and there's some other things as well, but for our purposes here, P waves and S waves. P waves are the fastest, can travel through anything. S waves, roughly half the speed, will not travel through liquid. I talked a minute ago about how we know the outer core of the Earth is liquid. This diagram sort of shows it. So that bright yellow zone within the Earth, that's the liquid outer core. So up at the top of the diagram, you have an earthquake. It sends off P waves here on the left. Those P waves travel through, in this case, the orange mantle. One thing that waves do when they encounter rock of different density is they can bend or refract. And P waves will refract when they hit this dense metal core. And it will move the core. And you actually get little areas that don't have P waves because the outer core is refracting them. But look at the right. That's the S wave. S wave does not travel through liquid. So when it encounters this liquid outer core, they just die. So you get this big zone called the shadow zone on the other side of the Earth that doesn't receive any S waves at all. If that outer core was bigger, the shadow zone would be bigger. If the outer core was solid, you wouldn't get any shadow zone of that size at all. It might refract like you see here in the P wave, but it wouldn't be completely dampened out as it is here. So earthquakes, we think of them as being things that are bad. They hurt people. They topple buildings. They're also a bit like a CAT scan of the Earth. It kind of tells us what the insides look like. So they can be useful too. Yeah, question. What's that? What's the mantle made out of? The mantle is solid rock. It's kind of dense. If you picked up a rock here, just an average rock here on the continent, it's going to be 30 to 40% heavier or denser. It's dense rock. I don't know if you've seen the gemstone peridot, green. That's the mineral olivine. There's lots of olivine in the mantle. There's lots of garnets in the mantle, these really dense minerals. So it's just dense, dark rock. But it behaves plastically if you go down deep enough. So it's a little different than what we have here on the surface, but it is solid rock. Yeah, what else?
I was always told that the mantle was like all lava.
Is the mantle all lava? Absolutely not. Or what would the shadow zone look like? I mean, the whole thing would be a shadow zone pretty much, right? This S would be able to go through the core or through the crust, but nothing else. There is some liquid in the mantle, but the only liquid is melted rock near areas where we have volcanoes. And it's right near the top of the mantle, and it's really localized. It's really small. The mantle is mostly solid rock. Let's see how much time. We'll stop here. This section's kind of cool. Now we'll get into the death and destruction next class. So have a good weekend and good luck with all that smoke out there.